For f of x equals x squared and g of x equals x squared plus 9, find the following composite functions and state the domain of each. The first one we're going to work on is f composed with g. F composed with g of x is an operation that substitutes one function inside the other function. F of x being written first is going to be our outside function, and g of x second is our inside function. So we can rewrite this as f of g of x. So we're substituting a g of x inside f of x, and g of x is x squared plus 9. So everywhere we see an x in the function f, we want to change that x to x squared plus 9. So that becomes x squared plus 9 squared. We want to simplify this to be x squared plus 9 times x squared plus 9. Multiply that out, we get x to the 4th plus 9x squared plus 9x squared plus 81. And we can combine like terms. 9x squared plus 9x squared is 18x squared. So f composed with g of x is x to the 4th plus 18x squared plus 81. And then for the domain, because our two original functions are polynomial functions, their domains are all real numbers. So the domain of f is negative infinity to infinity. The domain of g is negative infinity to infinity, are all real numbers. And when we did the composition, that also created a polynomial function. So the domain of f composed with g is negative infinity to infinity, are all real numbers. Now let's find g composed with f. So g composed with f of x is going to be g of f of x. F of x is now the inside function. And f of x is given to be x squared. So in the function g, everywhere I see an x, I'm going to change that x to x squared. So that would give me x squared squared plus 9, which is x to the 4th plus 9. The domain of g composed with f is also all real numbers, because composing two polynomial functions gives you a polynomial function. So let's find f composed with f of x. So now f is our outside function and f is our inside function. F of x is x squared. And we're substituting into x squared. So it's x squared squared, which is x to the 4th. This is also a polynomial function, so the domain of f composed with f is all real numbers from negative infinity to infinity. And finally, let's work out g composed with g. Of x. That's g of x. G of x was given to be x squared plus 9. And we're substituting that into x squared plus 9. We'll simplify. That's x squared plus 9 squared plus 9. And we worked out just a few moments ago what x squared plus 9 squared is, so we can use that information so we don't have to do it again. To x to the fourth plus 18x squared plus 81 plus 9, which is x squared plus 18x plus 90. And also this is a polynomial function, so the domain composed of g composed with g is all real numbers, negative infinity to infinity. Find functions f and g so that f composed with g equals h. And we're given h of x equals 6x plus 6 to the 8th. So we want to find these individual functions f and g that would, when we compose them, would create h. So we have to keep in mind that composition is substituting one function inside the other function, and f is our outside function and g is our inside function. So when we're looking at our h of x to find what pieces would work together, because we have an inside and an outside function, it'd be helpful to notice when something is inside a parenthesis, inside a radical, inside an absolute value, maybe in the bottom of a fraction. That's an easy thing to make your inside function. So we're going to make our inside function 6x plus 6. And then on the outside, we have this to the 8th power. So we're going to make our f of x, our outside function, x to the 8th power. So that when we compose f composed with g, we're substituting that 6x plus 6 in for the x in f of x. So that becomes 6x plus 6 to the 8th power when you compose it. For the function on the right, really below, determine whether the function is one-to-one. So first we have to remember what one-to-one means, what the definition of one-to-one is. And the definition of one-to-one basically says that if you have x values that are different from each other, then you should have y values that are also different from each other. So we have some different x values here in the domain, and these lines drawn are what y values they correspond to. And you can see that each y value is different, and so every x value is different, every y value is different, and so we do have a one-to-one function. So yes, this function is a one-to-one function. The graph of a function f is given. Use the horizontal line test to determine whether the function is one-to-one. So for a function to be one-to-one, we know that if the x's are different, then the y's should also be different. And the horizontal line test is one way that we test for this one-to-one definition. So what we do is we draw horizontal lines on the graph, and we're looking to see how many times these horizontal lines cross the graph. So we notice on this one that our horizontal lines only intersect the graph in one place. And that means that we're getting every time different y values. If we had an example of maybe a parabola, and we draw a horizontal line, that's crossing the graph in more than one place. If we think about those ordered pairs, those ordered pairs would have two different x values. We're going to say x1 and x2, but because they're on the same horizontal line, they are going to have the same y values. So that violates the definition of one-to-one, where if the x's are different, the y's should be different. So when we do the horizontal line test, if something is going to be one-to-one, we should only have one place where that horizontal line is crossing the graph. So for this example, the horizontal line test passes, and this graph is a one-to-one function. Find the inverse of the one-to-one function. State the domain and range of the inverse function. So this is a one-to-one function, and that means that the inverse will be a function. To find the inverse, we need to switch the x and y coordinates. So the inverse function will have an ordered pair that's -13, -4. So that's switching the x and y coordinates for that ordered pair. Another point would be -10, -3. That's switching the x and y value for that ordered pair. 11, -2 would be another point on the inverse, switching those two x and y values. 15, -1 is another one, switching this x and y value. And then 14, 0, switching this x and y value. So this is the inverse of the one-to-one function. The domain is defined to be the set of all first coordinates or x values. The x values for this inverse are -13, -10, 11, 15, and 14. The range is the set of all second coordinates or y coordinates. That's -4, -3, -2, -1, and 0. So that's the domain and range of the inverse function.